Everyone, I'm back with another video in which we will be reading a research paper. So without wasting time, let's back into it. Usually when we train large language models, we predict text one word at a time. But what if we ignored words and just predicted letters, the raw characters? That's the challenge this paper takes on. Character level language modeling with deeper self-attention. Published by Google AI in 2019. A late behind, yes, I guess. And here's the surprising part. They showed the transformers, the same architecture behind today's ChatGPT and LLaMA, can beat RNNs, obviously they can, at this difficult task. Let's break it down step by step. So imagine you are trying to read a book letter by letter without knowing where words begin or end. That's basically character level modeling. This paper built a giant 64-layer transformer that learned to do exactly that. It achieved record performances on benchmarks. The key trick? Extra training signals, kind of like giving a student practice questions at every step instead of only at the final exam. That's what made such a deep model possible. So, why it is hard? Because when you work with raw characters, the model has to learn everything from scratch. Spelling, grammars, even when one word ends and another starts, the older model like LSTM and RNN were the champions here. They read one character at a time and carried memory forward. But that memory was short, usually less than a paragraph. Transformer changed the game. Instead of passing memory step by step, every character can look back at earlier ones using self-attention. Here's what they look like. You can see the image. Each dot is a character. Notice how arrows only point left. That's the casual mask. It means the model can only use the past and never peek at the future. The red arrows show the main goal predicted the next character. Now, think of a task as a guessing game. You have seen, let's take an example of hello. You have seen HEL and you're trying to guess the next letter. That would be probably L and next would be O. Then you guess the next and so on. Mathematically, the model says the change of a full text is equals to product of guessing each character one by one. So the architecture is just a tall stack of transformers. That's a 64-layer deep. No loops, no recurrence, and just attention. So here's the problem. Like everything has a one problem. So here's the problem is training such a deep transformer usually fails. Like trying to train a skyscraper-sized neural net, the signal gets lost before reaching the top. Obviously it would. So the authors invented 3 clever tricks called auxiliary losses. These are shown in these 3 figures. Let's understand these. So first, instead of predicting only the very last characters, the model also predicts every intermediate one. That's like giving the student puzzles quiz at every pages, not just at the end of the book. As we have learned in our previous classes, we have all things in the after every chapter we have quizzes, questions, and all things. Secondly, they made even the lower layers make predictions, not just the top of the tower, but floors in the middle too. These extra signals help the model learn faster. Later in the training, they slowly remove these training wheels. Then thirdly, each possible predicts not only the next character, as you can see here, but also the few steps into the future. For example, if the input is shine, the model doesn't just guess if we input just SHI, then the model just don't guess the N, but also predicts the E. This teaches it the plan ahead and learns higher patterns, the more richer patterns. So one issue with transformer is position. They don't know whether a character came first or last unless you tell them. So the original transformer was using sine wave signals to encode positions, but in 64 layers that weakens. So here's they gave each layer the own learned positions, like positional signals, giving each floor of the skyscraper its own sense of order. Then they tested on two datasets, that is text8 and NVK8. Text8 is 100 million characters from Wikipedia, cleaned down to just 27 letters. Yeah, it's a huge less amount, to just 27 letters and symbols. Then the NVK8, that's 100 million bytes of raw Wikipedia with 205 unique symbols. The model was huge for 2019. 235 million parameters. It took 175 hours on Google TPU to train. Yeah, that's a quite huge. 175 hours on Google TPU to around quite a lot of days. That's a week straight for computing, obviously, yes. So here's the result. This table shows like older RNN models like LSTM scored around 1.25 bits per character. The 64-layer transformer scored 1.13, much better. Even the smaller 12 layers version beat the RNN. This was the first clear sign that transformer was superior for this task. Then in this table they also tested context length with shorter memory, only 32 characters. Performance were weaker, but with longer memory, 512 characters, performance improved a lot. This shows why transformer, which can look far back, shines here. Obviously, everyone is shine. So, this table, that's table 4, to see what mattered, they removed tricks one by one. Without predicting multiple positions, the model complexity collapsed. Without intermediate losses, performance dropped, and positional encoding helped quite helping. So the big wins come from those extra prediction tasks. Without them, deep training wouldn't work. So the results of NVK8 are on the harder NVK datasets, the transformer again won. RNN hovered at like 1.23 while the transformer hit 1.06, like 0.17 high, like lower. That's a massive improvement and the new state of art. They also tested on the word level benchmarks. Words based models still did better at the time, transformer at the character level weren't there yet. But the important thing was character and byte level transformer were now possible, and this opened the door to today's models that handle text and multiple granularities. So, they also checked how the model behaves, give it as a prefix like I would say an example of PROV and predicts like completions, proven, probability, नहीं probability won't provided or probable. Yeah, probable would work. That shows it really learned spelling and morphology. So even more impressively, it remembered a fake name across 434 characters, more than a page of a text. RNN could never hold memory that long. That's the real power of transformers, long range memories. So, what did we learn till now? This paper proved that deep transformer could beat RNNs at character levels. Modeling with tricks the auxiliary losses and positional embeddings, they could scale up to 64 layers. It showed the transformer can track dependencies across hundreds of characters, something RNN struggled with. And in the hindsight, this was one of the stepping stones to today's large language models, from predicting characters in 2019 to predicting everything in 2025. This paper have helped pave that way. So thank you. I will back again with another video. Thank you.